Okay, great. So thanks so much to Rel for the invitation to speak at this Paradigm Summer School. And I'm going to go to here. And so I'm going to tell you today about, is this working?
Yes, sure.
It even vibrates.
There you go.
Oh, great. Okay, thanks. So I'm going to tell you today about our work on developing beta gallium oxide. And this actually, basically, we're going to try to go through really the key features that we need to make high performance devices. And so the goal in this research, if you work in semiconductors, you can sort of go into, maybe there are more avenues, but go in two avenues, is do semiconductor science and semiconductor physics and technical. But if you're really interested in semiconductors, of course, the real driver is always device technologies. That's actually what really gets the significant funding. And device demands are actually very, very serious in semiconductors because we're always working against the weakest aspect of the semiconductor. This is what we always work against. And almost everything has to be at least good enough. So I'll try to show you how much progress we've made in this new ultra-wide bandgap semiconductor beta gallium oxide today and tell you the stories. And I know there's exciting work here in Paradigm going on with germanium oxide. So hopefully, which I would like to also learn about a little bit today. So hopefully also for the folks working in germanium oxide can learn from some of our stories from gallium oxide. Okay, so this is a team, and I will try to give credit to the team members throughout the talk because professors, as all of you should know, as graduate students, if you don't do, professors sit in their office and bark out orders to the students. So we just sit in the command center. Our experimental thing is our very expensive reclining chair, barking out orders to the students. You do all of the work. We sit in our offices. Okay, so I'll try to give credit to the folks that are actually doing the work. I'm going to start with a motivation. And this is a big picture motivation. And then I'm going to go through an introduction on this unusual semiconductor, beta gallium oxide, where we think its big application is high voltage power switching. And then I'm going to work through actually, so this is actually going to be device motivated, but some very basic material study, go through the elements of vertical power devices and transistors, some of the work in our own group on Schottky barrier engineering, field management with mid-K and high-K, and novel work where we're using mid-K. This is from a just graduated student from my group, Nolan Hendricks, who's at Air Force Research Laboratory in Dayton, Ohio. And I'll sort of circle back to the motivation with what we're really working on a new large RPE project that we're just starting right now. So where does your electricity come from? So like, where does the power come from this building? Maybe Tyrell, do you know?
Yeah, actually, it's 3 different independent power feeds from each one, which is 12 kilovolts.
Yeah, right. They're feeding at 12 kilovolts, but probably at the primary generating station. Right. It's probably being pushed up to the grid scale voltage, and grid scale voltages. Do any of you, when you see high tension transmission lines, do you have any idea what voltage they're at? Yeah. So maybe 300K to 600K in the US, somewhat more so in Europe and in China. They're megavolt and over megavolt transmission lines. Why? Because of the I squared R loss. So increase the voltage, decrease the current, you reduce it. So this is high voltage, okay? So at the power plant, you have to go way up in voltage. You have to step up in voltage, okay? So you have to have transformers, you have to go up in voltage. You may want to go AC/DC. There's many, many reasons to have a big drive, to have DC transmission that takes out a huge amount of problems, okay? But then you need to go back to AC, okay? So you need to transform and invert, okay? That's partly what power electronics is about. Another piece of power electronics, all of everything we do from data centers, okay, to your laptops, you have power electronics. Power electronics are everywhere, okay? And so they're going up in voltage, down in voltage, okay? Conditioning the power, AC, DC, DC, AC. It's everywhere, okay? And it's a huge area in efficiency. So I'm not a power device circuit person, okay? And I think coming to some of the themes of these schools, you have to really understand another big thing is valleys of death, okay? And these are really real. It's not just the catchphrase that Washington politicians come and go. Okay, it's a real deal. Okay, so I come from materials, and I've never had a course in device physics, but I'm self-taught in devices. I come from materials. I'm not a semiconductor physicist or condensed matter physicist. I'm self-taught in these areas. These are two things that I've taught myself in my career. So be willing in your careers to get out of your comfort zone and teach yourself new things by getting textbooks and working through them, learning by osmosis. You'll actually have a much happier time than if you just stay in your comfort zone, okay? In Mike Spencer, who's a long, great career in this, you'll hear about his perspectives just after lunch, and GaN and silicon carbide. I think that was Mike's title. In power electronics, you have to worry about the power semiconductor material. That's what I'm going to focus about today. Those materials are used in devices. So there's already a valley of death between the materials and the devices. The bigger valley of death is going from power devices to power circuits. And if you actually talk to a power circuit designer, they don't know semiconductors and they don't know materials. They want essentially a very complicated data sheet which has terminal characteristics. This is a huge valley of death, okay? Because when I talk to circuit designers, I realize they don't know anything about the materials, and they're also totally amoral when it comes to the materials. So if a silicon device works better than a GaN device, nice knowing you. Okay, and there's silicon devices that are very competitive with GaN, and so that's a problem. But between the power circuit designer and builder, there's also a valley of death to power systems. Okay, because the systems are very complicated. And the power system deals with the load and all the bad things that can happen on the load. And that talks back to the circuit. And it doesn't talk back in a nice way usually. Okay, and so there's actually another valley of death there. Okay, so quite often as a material/device physicist, condensed matter physicist, I'm talking to power systems people, and there's 2 or 3 valleys of death. And these are extremely serious. Okay, so the other thing in success is really understanding how you bridge these valleys of death, okay? A lot of my work throughout my career has been in the materials for gallium nitride, and it's been a very happy experience because the devices that I work on most extensively to this day are gallium nitride LEDs, and all these other valleys of death actually don't exist. Actually, almost everything comes to the discrete device performance. No circuit. The system issues are actually fairly easy to understand, okay? But when you get into power electronics, it's different. And so in your careers, you may really face these valleys of death. And learning how to bridge them can be disruptive, at least for your own career success. Okay, so here's a motivation. Okay, and the reason I ask you about the grid voltages. Okay, so the highest commercially available devices that are available today are either 6.5 or 8.5 kilovolt silicon IGBTs. This is a isolated or inverted gate bipolar transistors, or silicon thyristors, okay? The silicon thyristors, it's one device, so it's not nanoelectronics, it's mega electronics, and the devices are 6 inches or 8-inch wafers. It's a single device. It's holding in the off state, the reverse bias state, this voltage, okay? Huge voltages. And the highest rated are 8.5 kV, I believe, from Infineon, or at a little bit lower voltage. Maybe Mike will talk about this today, or 3.3 kV silicon carbide MOSFETs. And there's some push to get the voltage up, but I think it's a little bit problematic. And so to get to these huge ratings, so say we were working with 6.5 kV, the grid's at 650 kV, there have to be 100 devices in series, okay? Big devices, okay? And big devices. And then one of the issues, and this is where working with power systems engineers has been really rich and rewarding for us, is that these devices all have to be switched synchronously. Okay, and if they're not switched synchronously, excess voltage will build up on one of the devices, okay, and it'll fail. Okay, it'll fail because the individual voltage would have. And so this is a big push to actually going to synchronous switching, which means that the control circuits are actually optically controlled, where you can split the light, okay? And this is totally galvanically isolated. And galvanic isolation is something they worry a lot about, so that every device is switching synchronously without any galvanic feedback. When you do it electrically, which is what's done today, the power systems engineer spends a huge amount of time worrying about electrical feedback. ringing, okay, and actually fairly challenging issues. And so we're just starting. We're under contract and on our last snag with ARPA-E, a very large ARPA-E program called UltraFast. And don't worry, there won't be a quiz on this. What we're developing for our gallium oxide, this is all in conventional semiconductors where we actually have optically powered gate drive circuit, which is also optically controlled. Okay, so these are phototransistors, which are bipolar transistors where the base is actually, sorry, the base of the bipolar transistor is, instead of electrically contacted, it's actually optically controlled. This is essentially a solar cell, okay? This from Thor Labs turns out, just as after we proposed this, just turns out to be off the shelf. This we actually have some fairly hard design and epitaxial growth requirements. Over here, okay, is where we have beta gallium oxide. We'll have a transistor here, okay, which is beta gallium oxide, and we have what's called a freewheeling anti-parallel Schottky diode. So this is what we're working on in gallium oxide. This is what we're working on in conventional 3.5s. And then there are actually very hard testing requirements that are out of our expertise, but we have a great guy, Jin Wang, on our team from OSU, who's a power electronic circuit designer and builder. And then we have a test platform, and this is the load, okay? That's you using the power, okay? So that's what we're working on. And so what I try to do is take you to the story, convince you, and I'll show the two-device integrated circuit at the end of the talk, if I don't run out of time, that we can actually do this, okay? So that's the big picture of where we're trying to get to, so that this actually goes into real circuits, okay, that outperform any other semiconductor. So those are the hard requirements, okay? So we have to have absolute performance outperforming anything else. Our competition's in the room. It's silicon carbide. Our goal is to put you out of business, Mike. Send you to a happy retirement. Okay. So I'm going to introduce beta gallium oxide, okay? And so what is this crazy material, if you're not familiar with it? Beta gallium oxide is one of the remarkably promising ultra-wide bandgap semiconductors, okay? And so what we worry about in semiconductors quite often, this is comparing common semiconductor silicon, a little bit less common silicon carbide with gallium nitride, now the second most produced semiconductor in the world. Diamond, an emerging ultra-wide bandgap semiconductor, and beta gallium oxide is the bandgap. So this goes from the highest electronically occupied level to the lowest unoccupied level, okay? And that's the bandgap, okay? And the larger the bandgap, the better. And the dielectric strength of a semiconductor goes something like the bandgap, maybe squared. Okay, that's not fundamental. And then we usually refer to this in something that's an ill-defined quantity, which is called the breakdown strength. Okay, and the breakdown strength, if you look at silicon, it's about 300 kV per centimeter. So 1 centimeter thickness of material could hold up 300 kV of material. The silicon wafers are a fraction of a millimeter thick. This is why you have to have many, many, many silicon wafers stacked to get to the high voltages we referred to, okay? And beta gallium oxide has a predicted dielectric breakdown strength on the order of 8 megavolts per centimeter. So this is something about a factor of 30 times better than silicon, which is a competition, and about a factor of 2x or 3x higher than the competing wide bandgap semiconductors, silicon carbide and GaN. And I'll explain some issues with diamond in just a few moments for you, okay? What makes beta gallium oxide remarkable, and this is why I'm so interested in the work going on here and at Michigan and elsewhere in germanium oxide, is that beta gallium oxide can be grown directly from the melt. And until the work, I think the bandgap of gallium oxide is just a hair larger than rutile germanium oxide. So I think it's a fair statement that beta gallium oxide is the widest bandgap semiconductor that can be directly grown from the melt, okay? Silicon carbide, which is a remarkable semiconductor, cannot be grown from the melt. There's no liquid silicon carbide that you can pull single crystals directly, okay? So silicon carbide is grown by essentially a sublimation-like or CVD-like process. GaN cannot be directly grown from the melt, but just in the last year or two, there's huge progress, really just in the last year or two, from work that we were involved at the early stages with the monothermal growth of GaN. But there's no direct melt growth basis of the silicon, of course. is the largest, highest quality single crystal that's grown. Large single crystals that were actually developed for 18-inch technology. The 18-inch technology failed. We're probably on the order of the heights of this room, with boule diameters probably on the order of closer to 24 inches, 20 to 24 inches, okay? And so that's one of the great things about silicon technology. So beta gallium oxide can be grown by the Joukowsky method, but the preferred method right now, which produces the substrates that are used for almost all the device research, are grown by the edge-defined film-fed growth method, okay, EFG method. This is also used by some companies to grow sapphire, okay? And this produces slabs that are on the order of, say, half a centimeter to a centimeter to a few centimeters thick, but in the long direction, the slabs can essentially have any dimension. So this has already been commercially available at 4-inch, demonstrated at 6-inch and 8-inch. This lateral dimension can keep scaling with the EFG method. The preferred method would have Joukowsky growth or vertical Bridgman growth for these crystals, because in principle, those techniques will have less loss of the crucible material. One of the worries in our field is that the iridium loss, these are grown from iridium slits in iridium crystals. The iridium loss is actually a cost limiting factor. So iridium is actually, and so we're still considering what would be better growth techniques that are lower cost, okay? And then this just gives you a survey. If we have these kind of breakdown strengths with these kind of crystals and many other things that I'll talk about today, the kind of technologies that we would move into, but either in direct high voltage technologies, but where we're mostly interested is looking at grid scale technologies, okay, going from low voltages to very high voltages for the devices. Okay, for those of you that, and probably most of you are not familiar with beta gallium oxide, so quite often people say, well, what's the crystal structure of beta gallium oxide? And the answer is the beta gallia structure, okay? So it's a unique structure. It's not a simple deviation from any other crystal structure. Half of the gallium cations are in tetrahedral sites, shown with the green tetrahedrons here, and half of the gallium cations are in octahedral sites. So there are two unique gallium sites in the crystal structure. It's monoclinic. It's very monoclinic. It has a short B axis, a fairly large C axis, and a huge A axis. I'll show the lattice constants in the next slide. And then it has 3 unique oxygen sites. And then there's 2 primitive unit cells in this non-primitive monoclinic structure, okay? And so if you work on this and you're a graduate student, you need to take a little bit of work in crystallography to get familiar working with the lowest crystal system symmetry that you can work with and stay sane. Don't ever work with triclinic. Your thesis advisor was my graduate co-advisor. Yeah, yeah, Bernie Wunsch. Yeah, at MIT. Yeah, okay. And so I always forget the numbers, but so the A lattice constant is about 12 angstroms. The B lattice constant is very small. It's about 3 angstroms, and the C lattice constant is about 5.8 angstroms, okay? So, and the beta angle is significantly different than 90 degrees. So it's really monoclinic, and it's really not like any other crystal structure. Something else we'll talk about today is the EK diagram. And so this is in reciprocal space, and this is just in different directions in the Brillouin zone. Again, this spaghetti down here is because of the complicated crystal structure, okay? And so you go directly from orbitals to bands, and because you have low symmetry, you have a lot of bands, okay? And the highest occupied bands are the valence bands. And on the landscape of EK diagram, this is approximately flat, okay? And the curvature of the bands, okay, directly determines 1 over the curvature of the effective mass of carriers. And because the bands are flat here, if we had holes in beta gallium oxide, they would be extremely heavy. And from a lot of experimental work and theoretical predictions, if we do take an electron off of the valence band, which are really coming from oxygen 2p orbitals, okay, there's a local lattice relaxation that happens on a very short time scale. I've been involved in collaborations on experiments that we actually determine the time scale that there's a relaxation into strong polaron states, okay? And so the holes are very heavy, and then the lattice, okay, if we ionize and have an empty state in the valence band, immediately relaxes around that hole and forms a heavy polaron. Okay, and that happens on vibrational timescales, which are picoseconds. Okay, and that's experimentally measured with my collaborator Saulius Marcinkiewicz at KTH in Stockholm, and that's on the order of half a picosecond. Okay, what you would expect for the motion from acoustic phonons. Okay, and so now we're going to look at on seeing how, if we have these properties that I showed a couple slides ago, on how we look at possible figures of merits for power switching. And these are tables from a very important paper from 12 years ago from our colleague Masataka Higashiwaki, who spent until very recently at a national laboratory in Japan called NICT, National Information Communications Technology Laboratory, but he just moved to Osaka Metropolitan University, where he has a wonderful start there. And this is a key paper from 12 years ago in APL, because what Masataka did is he looked at comparing, everything's referenced to silicon, comparing wide bandgap semiconductors, silicon carbide and GaN, beta gallium oxide, emerging ultra wide bandgap semiconductors, aluminum nitride and diamond. So you see the band gap going up here, and this looks at electron mobility, predicted using this sort of parabolic square law for breakdown strength. And then he put these into what's called a figure of merit from Jay Balaga. This is something that Jay Balaga at NC State developed a little bit over 40 years ago. In fact, he probably developed this when he was working at GE Research. And this is looking at essentially how you minimize the on-state resistance while holding a large off-state reverse bias voltage. And everything is referenced here to silicon. And so the mobility matters, the dielectric constant matters, but what really matters is the breakdown strength, and this goes as the cube of the breakdown strength. And so if you throw these numbers here, here, here into this FOM and then normalize it to silicon, because this will have dimensions, but everything's normalized to silicon, okay, you'll find that ultra wide bandgap semiconductors for the drift regions, for the on-state, minimum resistance, and the ability to hold off-state voltage look extremely favorable. I mean, 3 orders of magnitude, almost 4 orders of magnitude better than silicon, okay? And then very typically in power electronics, folks make these plots of the on resistance and the dependence of on resistance on breakdown voltage. This should never really be shown as breakdown voltage. There should be a design blocking voltage for reverse bias. Then one should be able to predict the on resistance, okay? And so in these kind of plots, and then usually the data is put on scatter plots versus what's called the fundamental limits, which are these lines for different semiconductors, okay? This is sort of what goes into bragging rights for the device performance, okay? And so these plots are used quite often in power electronics literature, okay? And so the way you derive this is essentially, it's just an exercise in Gauss's law, okay? And so from Gauss's law, the slope, okay, if you deplete a semiconductor, is given by essentially the net doping, okay? And so this is going to be usually n-type. So this is and net refers to the concentration of donors minus the concentration of unintentional acceptors. And then usually you work with a triangular field, which means there's actually curvature, okay, if you look at the band diagrams, okay? And so this is fine, and this means if we want to go to very, very high voltages, the voltages, okay, are going to be, this is electric field versus distance, okay, and so this is how you get to the voltages, and you go through a little bit, okay, of arithmetic, and you come up with these equations. The problem with this analysis originally, when Jay Balaga did it over 40 years ago, is that he assumed that all the dopants were shallow. And at the time he was developing his figure of merit, which is a remarkable figure of merit, he was working on semiconductors where all the dopants were shallow, okay? And so this is really what he did. But if you look at new wide and ultra wide bandgap semiconductors, we may not have shallow dopants. And the mistake that many folks have used, including the plots in the previous thing, is they don't account for the dopant ionization. So the on-state resistance actually depends on the available measured carrier concentration, N, times Q times mu. This is the conductivity. The resistance, okay, is 1 over the conductivity times the thickness of the semiconductor. This is actually what gives you neon resistance, okay? For hydrogenic dopants, which follow hydrogenic doping models, the electron concentration is at room temperature is typically very close to the net doping, okay? But if we have deep dopants, this is not the case. And so what Yue Zhang and I came up with is a modified figure of merit, which just accounts for the dopant ionization. In reverse bias, the assumption is that everything is dumped and you end up with this triangular field profile. So the ionized impurities in reverse bias, we assume everything is ionized, but in forward bias, you're up against ionization, energy, and temperature. And so if you look at comparing, again, this series of semiconductors, because these are the 3 semiconductors, and germanium oxide should now be added to these kind of tables and analysis, okay? We're very worried about the donor ionization energy, okay? And the beauty for gallium oxide is that we actually have hydrogenic dopants with ionization energies that follow almost exactly what's predicted from hydrogenic models of doping, okay? Aluminum nitride, which is a very hot topic right now, does not have hydrogenic dopants from any credible work. And diamond, the shallowest dopants are not for the N-type material, they're actually for the P-type material, and the dopant ionization is about 370 MeV, okay? Interesting is silicon carbide, it's not quite hydrogenic, okay? It's a little bit deep to be hydrogenic, okay? But that still 60 MeV actually turns out to be a fine number for silicon carbide. And when you look at this, and you look at the dependence of electron concentration on net doping, and in these plots, okay, we compare silicon carbide, GaN, aluminum nitride, diamond, and beta gallium oxide. Here, we put a lower limit, which are these points, which are the cleanest materials that we can find in the literature. So we've actually accounted for the unintentional acceptor doping, except in the case of diamond, where this is P-type, and this corresponds to the unintentional donor doping. And aluminum nitride and diamond are actually not very clean semiconductors, even today at the state of the art. Aluminum nitride is still not very pure compared to where we are in GaN or compared to silicon carbide or silicon, okay? And same comments on diamond. And so what you find is that you can dope, that's fine, over a range. There's a lower threshold where you can actually dope effectively, and that's sort of given is the stop points on these plots. And below that, you can't get controlled doping. That's just the reality of materials growth. This is where we fight very hard, okay? And then what you'll find is that for the materials with hydrogenic dopants, which are these, okay, you find almost a 1-to-1 correspondence between measured electron concentration or predicted electron concentration and donor concentration. When you take this factor of doping inefficiency into account and then remake these FOM plots, what you actually find is that beta gallium oxide for highest voltage is predicted to be the lowest resistance semiconductor. Okay, that's the big win for gallium oxide. So we're also very interested where germanium oxide would fall out in these analyses. Okay, and so you might start getting a feeling that these numbers really matter. Okay, so now I'll ask you a quiz. What's the atom density in any dense inorganic material? Any dense inorganic material. How many atoms per cubic centimeter? That's the cubic centimeter. But if that was silicon or GaN or silicon carbide, it doesn't matter. It's always within a factor of 2 because bond lengths are always about the same, right? So if you do the math very quickly, you're going to find in 1 cubic centimeter of material, there's about 0.1 Avogadro's number of atoms. It's always about 4 to 8, 4 to 10 times 10 to the 22 atoms per cubic centimeter, okay? But always, you'll get that, okay? Number, okay? Gallium oxide is, I think, 8 times 10 to the 22 atoms per cubic centimeter. GaN is very similar to it because atom spacings are all approximately the same, okay? And so what do these numbers mean in terms of purity? So if I have purity level in the mid 10 to the 16s, how pure is that? part per million, right? And a part per million for power electronics sucks, okay? Power electronics, you need to be closer to parts per billion, okay? Silicon carbide is ultra pure. Silicon carbide approaches towards parts per trillion, right? Okay, am I getting that right, Mike? Parts per billion, sorry, okay? Silicon towards parts per trillion, germanium, because of float zone growth, even purer, okay? So purity in semiconductors is paramount, okay? In everything I do, I worry about impurity concentrations of unintentional impurities, at least in the parts per million level, okay? And for a lot of things I do, I worry about probably 10 times worse, okay? This isn't just for power electronics. This is the work I do in non-radiative recombination in semiconductors, okay? So the lesson in semiconductors is that you have to be ultra pure, and the synthetic routes have to be ultra pure, okay? So that's a takeaway message, okay? So again, think of this as a little bit more than a part per million. Think of this as a part per billion, okay? At 10 to the 14th, okay? And so we'll come back to that in a moment. Another takeaway message, when you see plots like this, I tried to take the plots of this out, but here's a typical scatter plot of different generations, silicon carbide MOSFETs, but looking at the on resistance and the dependence on breakdown voltage. And then people will throw all their data points on this, like this. And you'll see plots that are populated with all data points in the literature. And typically, they will always be far away from the predicted performance, okay? But the reason, and this is why it's a very nice paper from the late, great John Palmer from Cree, which became Wolfspeed, okay, is that you can actually take into account the access resistance, not the drift region resistance. And then if you get really good device physicists analyzing their data, and this is one of the very few cases you'll see this in the literature, they will actually include all access resistances, parasitic resistances, or derating on the blocking voltage. But what's very interesting is that when you go to very, very high voltage devices, and they're very exquisitely engineered, you will actually come to the theoretical limits, okay? And this is where we're hoping to get in gallium oxide. Silicon carbide folks have done a remarkable job of this. Okay, and just to show you where we need to get in gallium oxide for voltages, because we really believe it's in the 10 plus kV regime in our semiconductor beta gallium oxide that we can start outperforming any other semiconductor. And that means that we need to have controlled doping, okay, in the low to mid 10 to the 15ths. And this has to be intentionally controlled doping in this range. So this is on the order of less than on the order of 10 to 100 parts per billion, purity control, okay? And so that's kind of what we're fighting with, okay, for purity. And these have to be in extremely thick epitaxial layers. Okay. So now to change to the substrate issue, okay? And I'll tell you a parallel story. I was very fortunate because I have an outstanding group of colleagues at Santa Barbara, UCSB, starting in the early 90s because of Steve Denbars, came out of a colleague of mine at UCSB, came out of LEDs, and he heard of this guy in Japan named Suji Nakamura, who was solving the last color problem in LEDs. He was making blue LEDs. And this had long been the holy grail in visible light emitting devices, was to get to these short wavelengths, because there were green technologies that weren't very good, but they were sort of good enough. And red technologies by the early 90s were very rarely developed in conventional 3-5 semiconductors, but blue was the holy grail. And Suji Nakamura in Japan had sort of cracked the nut on how to grow high quality GaN and solve the active regions in indium gallium nitride to demonstrate a disruption in blue LEDs. Okay, and so we started on this as early as 93, 94. And so I've worked on GaN LEDs with Steve Denbars, and then on many aspects of the electronics with Umesh Mishra at UCSB from the nascent days of the field. And what we did not have in gallium nitride at the time was a native substrate. So we grew on foreign substrates. And the foreign substrate of choice is sapphire or silicon carbide, and it leads to a very dislocated semiconductor. And my formal training is in transmission electron microscopy and dislocations. So it's been extremely lucrative for me because we have this defective semiconductor and I know a lot about dislocations. It's been great. But it's so slowed the progress in the field because even though many folks wouldn't admit it, we were always facing materials quality issues because of the dislocations. Now comes a semiconductor, beta gallium oxide, that has melt-grown substrates. And these substrates, they're not as good as silicon or germanium substrates, but they're not far off the quality of gallium arsenide substrates or indium phosphide substrates or gallium phosphide substrates. And this has enabled an incredible pace of the field. So if you have native germanium oxide substrates, it'll go very fast, and you'll find out if it looks good as a semiconductor or not. But you won't be plagued by heteroepitaxy on foreign substrates. That was really slowed the progress in gallium nitride. I think the field would have gone much, much faster if there had been a breakthrough in substrates and they're widely available. Okay, so just to tell you, this is a photograph of a 4-inch, probably 001 oriented beta gallium oxide substrate from novel crystal technology in Japan. These are commercially available, exceptional high quality. Okay. This is the leading substrate supplier in the world. There's very serious effort in the US at Synoptics, which was a laser host crystal company acquired by Northrop Grumman, Saint-Gobain in the US. Advanced research at IKZ. Today I learned there's research here going on. There are many academic efforts. There's very good efforts in China on bulk growth of the substrates. So to first order, the substrate problem is solved. The cost issues may not be solved, okay? But the availability has really led to remarkable progress in the field. Okay, so I'm just going to take you through some different examples of things that we have to have in devices, okay? I'll talk about contacts, and I'll tell you about doping, and I'll tell you about etching. These are all things that we have to have. I'll tell you a few other things, and I'll give you some device examples, okay? In semiconductors, we generally want it, if we have diodes, we like to have Schottky diodes, very simple 2-terminal device where we have a heavily doped base region for high conductivity. We want to make a good ohmic contact to this, and we have a very lightly doped region. If it's a Schottky diode, we would not have this structure here. This is just a prototypical vertical 3-terminal device. We would just have a Schottky contact, okay? And usually the Schottky quality is determined by what we call the ideality factor, okay, and how close we also come to the predicted reverse saturation current, J0. So and then I'll show you ohmic contacts. And this is work, a lot of it from Steve Ringel's group, who's part of a MURI that I lead at UCSB, okay, showing a wide range of metals, okay? And these papers came out very early in the field. And many of the folks working in this field came from gallium nitride, and gallium nitride on foreign substrates. You would never see JVs for Schottky diodes that look like this. You might see a little region in the log current density dependence on diode bias where it's linear, and then you would see leakage, okay? These diodes are phenomenal right out of the box, okay? And ideality factors in the very best diodes in literature almost approach 1 perfectly, like 1.01. So these are great numbers. And these are linear down to the noise floor of the detection. But I've seen data where I'm more careful, either on larger devices or more careful current meters, okay, that might be linear over 10 to 12 orders of magnitude, okay, with ideality factors. So the diodes are fantastic. There's a wide range of Schottky barrier heights to work with, and I'll talk to you about some of the work that we're doing in our group on increasing the Schottky barrier height or decreasing the effective Schottky barrier height, okay? And then either with implantation or just using low work function metals with beta gallium oxide, we can get outstanding ohmic contacts. So very early in the field, we had outstanding contacts, both Schottky and ohmic contacts. And this was really a very pleasant surprise, particularly for folks who had never seen this because they'd already worked on defective semiconductors, and they always get very, very leaky diodes. And so that's been a very pleasant surprise. I'm not going to dwell so much on the growth plane, but this is still something in the field we spend a lot of time. And the analogy is here you have a new semiconductor rutile, germanium oxide, Probably you want to grow at 101, okay? Maybe, okay? And if you have a new semiconductor and you can get single crystals, and you say, great, we have everything. Then the next thing, an epi grower, you go talk to an epi grower, and they're going to say, what plane should I grow on? Or, okay? And then fine, so you roll a dice and you start picking some planes, and all of them have a different personality and epitaxial growth, okay? And then it gets worse, okay? And I spend a lot of my career on this, okay? When you finally selected the best crystal plane, usually the metric is sustaining planar morphology during growth. Even better, step flow growth or layer by layer growth in the growth. The next thing, the epigrower, and that would be me, say I want to have systematic miscut studies, okay? So I want to know the intentional miscut of the substrate because that affects the step terra spacing and whether I'm in step flow growth or layer by layer growth, okay? And then this consumes a lot of boule, okay? Because these have to be wire sawed on a precision goniometer. And then also in an intermediate step, the CMP polishing has to be developed. And all the residual CMP crud has to remove from the surface. Okay, suddenly you face all these issues, right? Just to get to the point whether you can see if the epitaxial quality is worth pursuing. Okay, so if you're getting a germanium oxide, that will come. These issues are far from fully resolved in gallium oxide. Okay, in GaN, they were largely resolved because Suji Nakamura started growing on all orientations of sapphire, and he found, not based on morphology or anything in microstructure, he used electron mobility as his metric, and he found the optimal miscut for sapphire. And then many subsequent studies, it turned out he really had found the right miscut. Okay, but that's a lot of experiments. It's a lot of volume of material consumed and a lot of cost. Okay, for the drift regions and the kind of devices that we're looking at, these have to be very thick. Okay, and so the numbers we like to use is that the breakdown voltage of gallium oxide is 8 megavolts per centimeter. If you talk to folks in the power electronic devices, they will immediately derate this by a factor of 2 because they're high field regions, okay? Whether they're geometric changes in a device, like there's a field spike here, the edges, so they'll immediately do a factor of 2 derating. And then if the electric field profile is triangular, there'll be another factor. Maybe we can work with 2 megavolts per centimeter is design principle. That means 200 volts per micron. Okay, so a kV is 5 microns, 10 kV is 50 microns, 20 kV is 100 microns. So suddenly we need exceedingly thick epitaxial layers, okay, that have sustained outstanding morphology, okay, and uniform doping. Okay, and so the preferred technique for having really thick drift layers is hydride vapor phase epitaxy, okay? And so far, this only goes so-so for gallium oxide. We would like to have high growth rate MOCVD. This is one of the frontier, both of these are frontiers areas in our research, but we need to have sufficiently high growth rate that it's meaningful both for how many hours as students you're willing to spend in the lab growing a crystal, okay? And then it's also economically feasible. HVPE growth rates can be astoundingly fast. Typically, when you think about MOCVD or molecular beam epitaxy, you think about growth rates of, say, a micron an hour or a few microns an hour. But HVPE growth rates can be tens to even hundreds of microns an hour, okay? And so the other thing at these high growth rates, okay, there's huge concern about having controllable donor doping, okay, with net donor concentrations in this part per billion to part per million range, and having exceptionally low compensating acceptors, okay? And then a lot of work that we've been involved with is actually deciding on the preferred donor. So you notice this goes straight down. There's carbon, silicon, germanium, tin. This is column 4 on the right-hand side of the periodic table. If we do these substitutions onto the gallium site intentionally, then these species that are allied onto the gallium site have 1 extra electron compared to the gallium site. So they may donate those electrons to be free conduction electrons, okay? So that's the typical criteria for donors, is that you look at adjacent rows in a periodic table to one of the host sites in the material, and hopefully you can then controllably put these impurities onto that site, okay, in very careful growth. And long story here is that this is a comparison of temperature dependence and the carrier concentration on Arrhenius plots. And this is work from Adam Neal at AFRL. Some of our materials are on this plot, probably the germanium materials, maybe the tin materials, our material, the silicon material. I can't remember where this came from. Okay, and then we don't fit the slope of these in an Arrhenius plot. We actually take this data and we fit it to an equation called the charge inequality equation. Okay, and the charge inequality equation, from that we can, because we have way more data points than fitting parameters, and typical of fitting parameters are the donor ionization energies, the donor concentration, and the acceptor compensating acceptor concentration. So this comes out of semiconductor carrier statistics. And then we can find, and it's very interesting, there is two slopes here, which is a strong hint that they're two donors. And all three of these species actually have two donor sites. We attribute this to the two different gallium sites in this crystal structure. So we have a shallow donor, which is what we call the hydrogenic donor, and a deeper donor, okay? And so far from all of the work, silicon is the most favorable because silicon primarily goes shallow donor site, okay? And honestly, folks that do TFT actually have a big fight with the DFT folks because they say everything should be hydrogenic, and it's clearly experimentally wrong because they're not. But I can't remember which one of the sites is supposed to be hydrogenic and which one's not hydrogenic. But the DFT folks can't get the right answer, actually. So that's been exciting. Silicon doping seems to be the most favorable dopant, but tin doping, which is where we've done a lot of work, is a very nice donor in MBE growth. And it turns out for what we do, an 80 MeV donor is fine. And this just goes through some of the issues in the donors, okay? And I took the slide out and now I regret it. The purest, and it's probably of at least interest to Mike, the purest gallium oxide that's been grown is by a company in Minnesota called Agnitron by MOCVD. And by doing exactly this analysis, they've realized controlled donor concentrations in the low mid to the 10 to the 15th. I'll show similar data from UCSB in a moment. And compensating acceptor concentrations now below 10 to the 14th. And silicon carbide, I think, Mike, the numbers of compensating acceptor concentrations in the cleanest silicon carbide are in the low 10 to the 13s, right? Yeah. And so we're actually in the same decade of material purity as silicon carbide. And that's been remarkable for us, for a semiconductor that's so young and has actually received fairly little attention. This is work from my colleague Sriram Krishnamurthy at UCSB showing controlled donor doping now down to the low 10 to the 14th, sorry, low to mid 10 to the 15th. And these are values that get us to the 10 to 20 kilovolt diodes that we actually need to develop, and just showing where we are in quality. And I think Sriram now has all of the records. It's really a hair splitting number in mobility, okay, in gallium oxide at room temperature. Okay, how are we doing on time? Okay, so let me tell you a couple material science stories. Okay, and this is tied to material purity and doping. Okay, and so the donors we intentionally put into the material to make it conductive. Okay, we either put in a very high concentration to have contact layers that we spread current, and we put down ohmic contacts. We do very light doping because these are the layers where we have either a junction, a Schottky contact, or some other structure that in reverse bias, we can deplete it, okay? And in forward bias, we have on-state conduction, okay? So we need very controllable light doping for donors, and that's in very good shape right now. It still needs work. We need very heavy doping for contacts, and that situation is very good. We also need acceptors. We're very skeptical with gallium oxide that we will ever have free holes and p-n junctions, okay? And I'm very interested in seeing what happens with germanium oxide. There's another wide bandgap oxide that 15 years ago was a rage topic of interest, and that's zinc oxide. And if you look in the mid-2000s, you'll see a huge number of papers on p-type zinc oxide. in some cases measured by very credible people in the field. The long and short of the story is that the p-type zinc oxide never existed. Never existed. And all these papers are wrong. There's no p-type zinc oxide, okay? No, there were many experimental papers. Yeah, there were many experimental papers on p-type zinc oxide, okay? It turns out that zinc oxide is what's called the surface electron accumulation layer, and it can make the material laterally homogeneous. And if you go into the nuts and bolts of the Hall measurements, you can have an N-type semiconductor, but if it's laterally non-uniform, you actually can get the wrong sign Hall voltage. And for sure, there was never p-type zinc oxide, okay? So it's an interesting story. And you will see in the literature, if you look at papers in p-type zinc oxide, you'll see the publications going up and up, and then you'll see it going down and down, and then bunk. And now, nothing. Yeah, it's a straight line at zero, okay? So there's no evidence in gallium oxide that we have a shallow acceptor. There's no evidence of a shallow acceptor, and that's a necessity really to have p-type doping. And the valence bands are extremely flat. So if holes form, you can always form holes in any semiconductor by just optically exciting with above band gap light. You'll create holes. But those holes in gallium oxide will immediately localize with the lattice, forming a strong polaron. So they're very heavy as free carriers, then they become that much heavier when they form polarons. But in semiconductor devices, we still need semi-insulating behavior, okay? And the substrates that are used today that are semi-insulating are either iron doped, okay, as a deep acceptor. So the iron level is somewhere in the gap. And if they're unintentional donors, they transfer their charge to the iron. The iron is miles and miles from the valence band maximum. You can't ionize electrons to it, okay? So semi-insulating substrates are typically iron doped. NCT also developed magnesium-doped substrates, but I think they sort of abandoned the magnesium in favor of the iron. Mostly, if you put transition metals into compound semiconductors from sort of the middle part of the periodic table, you'll get semi-insulating behavior. So chrome, vanadium, molybdenum, almost any of these things will lead to semi-insulating substrates. And if you have a good semi-insulating substrate, it's not clear which acceptor is better. But in GaN, where I work, there's still a lot of interest in developing improved semi-insulating substrates. In the last couple of years, manganese-doped GaN substrates are starting to look extremely promising, much better than the iron-doped semi-insulating substrates. So lots of reason in devices to have semi-insulating layers. If you're making lateral devices, like we've worked on a lot, making algo two-dimensional electron gases where you don't want to have any other conductivity. You want to have a semi-insulating substrate. There are a lot of device technologies where we want to have intentional semi-insulating regions, okay? This is sort of based something similar to a device my colleague at UCSB, Tomasz Misher, has worked on a cavet. This is sort of what a cavet design would like, where there's epitaxial semi-insulating layers, okay? And we have a lot of far out interest also in these acceptor doped layers. And so this is an example of what we do in our research. This is grown by my student Akil Maz, and very often we do what are called sim stacks, okay? And so we start with the substrate, okay? We grow material, then we open a shutter, so we actually have a flux of the intentional dopant, close the shutter. We are very worried about this concentration, okay? And this shows a nice example of controllable magnesium concentration over several orders of magnitude. We're very concerned about this rise profile, okay, and this fall profile in the structure. And this is something that we do routinely. We have a secondary ion mass spectroscopy at UCSB. So we sputter the material, and then we look at the ions coming off quantitatively into a magnetic sector SIMS, okay? So then quantitatively, with implant standards, get the concentration in the semiconductor. So this looks very nice. And then we can look at seeing if we have the dependence on Arrhenius plots of the magnesium incorporation with the magnesium flux. Okay, and this is just subliming off of solid magnesium. And so this all looks fine, Arrhenius plots, and we get the expected apparent activation energy for this. And it's very interesting. If we look at these profiles of as-grown material, we get, amongst friends, if I plotted this on a linear scale, you would see a beautiful top hat profile. When you look at a log scale, you start to see somewhat ugly surprises, but it's still fine. And if we anneal it at temperatures that might be used in process temperatures, we actually see the magnesium move. And the magnesium's really moving, okay? And these temperatures might be the process temperatures that would be used if there was a subsequent implant in the material to activate the implant. So these temperatures are not irrelevant for gallium oxide devices, because a lot of folks that come out of other device technologies can't resist the temptation to do the worst thing to a semiconductor, which is implant it and then anneal. Okay. And so the magnesium actually moves. And this is kind of remarkable. So you see, this is the magnesium concentration with increasing annealing temperature. So this is acting as a reservoir for the magnesium. This is going down. The magnesium's going out back into the bulk and to the surface. And at some point, it's going all the way through the substrate. Okay. And so we spent a lot of time puzzling on this. This is work I did with the modeling for this, is that for those of you who learned about diffusion, you know, the primary diffusion mechanisms are either vacancy-assisted diffusion or interstitial diffusion. Okay, so this is sort of what you learn in undergraduate material science. And at these temperatures, we could never account for the diffusion by being vacancy-assisted diffusion, which would be gallium vacancies. Okay, this never worked. Magnesium interstitials is a cation. It's a small cation. It's actually a fast diffusing species. But the problem is to take a magnesium on a gallium site and to place it on an interstitial site and to create a gallium vacancy. If you look at the formation energy of the process, this is very unfavorable. This is not favorable. And so what we proposed, and this was borne out in calculations, and what you learn in material science is that surfaces are always reservoirs of point defects. So the surface is always a reservoir of point defects, native defects, or sometimes extrinsic defects. Gallium interstitials are fast diffusers. And so what we proposed is that the surface is a source of gallium interstitials. Then we have gallium interstitials shuttling into the material. We have an exchange reaction at the surface with the gallium interstitial with the magnesium and the gallium. We have this exchange reaction, and then we have a fast diffusing magnesium interstitial. And this was borne out to be favorable in DFT calculations from Hartwin Peelers. And so that came out in a paper a couple of years ago in JAP that's referenced here. Okay. Now, another interesting story on acceptors, okay, and this goes to material purity, is that typically when we grow on semi-insulating substrates, we use semi-insulating substrates a lot. So developing semi-insulating gallium oxide here is important because for many electrical measurements, we want a fully resistive substrate. So all of our active layers that we grow, we can do good transport measurements without having concern about parasitic conductivity in the substrate. So it's essential for transport measurements. So we use semi-insulating substrates a lot in our research. And if you ignore these profiles, if you grow, and this is a little bit on the cold side, but still at sort of typical MBE temperatures, you'll get this long tail of iron from the ghost substrate into the film. And in the field, this was always attributed to diffusion of iron. But temperatures are actually quite low if you look at this for iron diffusion, okay? And then you notice if you grow colder and colder, you have less, and you say that's still consistent with diffusion because you're growing colder and colder, okay? But we had just completed around this time work on surface segregation in the material, okay? And if you actually anneal a film on a substrate at much higher temperatures than the epitaxial growth temperatures, okay, you actually don't find this profile changing at all at much higher temperatures than the epitaxial growth temperatures. So this profile really can't be diffusion because if we anneal at temperatures a couple hundred degrees C hotter than the growth temperature, this level should be going up. This edge should be becoming less well-defined. So it's probably not diffusion. So what we then looked at is that if we grow superlattices at high temperature, low temperature, high temperature, low temperature, what you actually find is that when you go to the low temperature layer, you have high impurity concentration. When you go to the high temperature layer, you have low temperature, low impurity concentration. And this is characteristic of surface segregation. So on the substrates that we have, there's free iron on the surface, and it's riding the surface with a very, very low incorporation coefficient. Okay. And so low iron concentration at high temperature growth, high iron concentration at low temperature growth. It's decreasing because we have weak incorporation here, we have more incorporation here, and we're actually consuming the material. Okay. And so if you fit this to models, okay, of the iron coverage with the surface, okay, it turns out that we have an initial iron concentration in these measurements about 3 times 10 to the 12. Now, if you take this 6 to 8 times 10 to the 22 atoms per cubic centimeter and take that to the 2/3 power, you're going to find that this number of a surface, you have about 10 to the 15th sites per square centimeter on the surface for anything. Okay, it's always on the number 1 to 2 times 10 to the 15th. So this initial coverage is only about less than 1%, 0.3% or less. And most of this is riding on the surface because the incorporation coefficients, this is the riding coefficient, is 99.3%, meaning per monolayer only 0.007% is incorporating. Okay, so I always emphasize this in the talks. Many people talk about the cleanest growth technique being molecular beam epitaxy, and it's been a technique that I've worked on throughout my career. The MBE growth environment is very dirty. It's not clean. It's not clean. Your surface is not clean. Your surface has junk on it. It's just riding on the surface and not incorporating. Okay. When people sell you MBE, it's the most perfect technique, and we can go layer, single layer by single layer, and I can take tweezers and I can put the atom here and stuff like that. Okay. And if you believe in it, you should legalize all everything. Okay. It's just not true. The growth surface is quite dirty. These are only things that we know because we can measure them. There's probably a lot of other stuff on the surface that never incorporates, and we can't measure it. Okay. We go to lower temperatures, and still most of the iron rides on the surface, but we get a little bit more incorporation. Okay. Now, for those of you that go into epitaxial growth, you learn, and if you really learn the classic literature, you look at Pierre Petrov's literature from Bell Labs from the 70s, where he does actually impurity capturing superlattices. Okay, and they're called smoothing superlattices. Okay, and in smoothing superlattices, you're actually doing high temperature, low temperature growth, or you're doing a refractory layer, non-refractory layer growth, and incorporating impurities, and you're actually purifying the surface by capturing the impurities. And you do this far from the active region in the growth, okay, in epitaxial growth, okay, and it's really impurity capture, okay. This superlattice that we developed here is an impurity capture superlattice because we can go from very high impurity concentrations down to very low impurity concentrations and completely consume all of the junk on the growth surface. And we're probably consuming a lot of other stuff, but we don't know what to look for in the SIMS depth profiles. Okay, so it's not bulk diffusion. So the whole literature always talks about the iron diffusion tail. It's not bulk diffusion. It's surface segregation with weak incorporation. Okay, let me tell you one more story. And do I have time for one more story? Okay, this is about etching. Okay, so when you see a nanofab, okay, or what UCSB we call it the nanofab. When I was in grad school at MIT, the fab was the micro lab. Okay, and I guess in your generation it'll be after Atto it'll be nano to pico fab. Yeah, the pico fab. Okay, so you know what do you have in fabs? Okay, you have lithography tools, right? And you have etching tools, right? And you have deposition tools, right? And the beauty of silicon and the beauty of most conventional semiconductors, gallium arsenide, indium phosphide, et cetera, conventional 3.5 semiconductors, and mini 2.6 semiconductors is that they have beautiful wet etch technologies. When one goes to wide bandgap semiconductors like gallium nitride, silicon carbide, Mike, you can correct me, okay? Aluminum nitride, diamond, we don't have wet etch technologies. We have dry etch technologies, okay? And dry etching is approximately like ion implantation. The semiconductor is always damaged during dry etching. There's always ion damage, okay? It's a problem, okay? And so one of the beauties of gallium oxide, and this is something that we've worked on, is that we actually have a wet etch technology. So these are fins in our effort to make FinFETs, okay, or trench MOSFETs that we make in a wagon wheel pattern. So we're in low crystal symmetry, so we make a wagon wheel with spokes going in a wide range of crystallographic orientation, so we can look at the crystallographic dependence of the etching, and then we dry etch the structures, okay, where we get essentially direct transfer with a hard etch mask on the structure. We get sidewall, visible sidewall etch features, and then into this, there's ion damage from the etching, okay? And if we make Schottky diodes on this, okay, then we get lousy Schottky diodes with large hysteresis, okay? So these are the sweeps in the Schottky diodes, okay, from the hysteresis, okay? And then when we do wet etching, it turns out that for gallium oxide, there's probably many other chemicals, but we use hot phosphoric acid, okay? And then we look at the temperature dependence in the etch, and then we look at the crystallographic orientation of the etch rates in these wagon wheel patterns, okay? So we can get controllable etch rates up to many microns an hour. So this is totally acceptable for mass production and fabrication. This is a totally acceptable process. The semiconductor industry lives on wet etch technology, okay? Particularly in compound semiconductors. I should make it just for those because the CHIPS Act, which is really about silicon technology, I have to make a big caveat about implantation and ion damage. Silicon as an elemental semiconductor, one can almost always completely anneal out the ion damage. In compound semiconductors, the ion damage creates interstitials and vacancies of all species. Usually one of those diffuses away too fast, and you can never recover local stoichiometry. This is why you can never fully recover ion damage, okay, in a compound semiconductor, okay? So here we can remove material below the ion damage from the etch depth, and then these are the Schottky diodes, sidewall Schottky diodes after wet etch, okay? We recover ideal diode behavior, okay? And this is a huge feature of gallium oxide that we have a wet etch technology, okay? So when you're developing a new semiconductor, you faced all of these things. You faced the bulk growth, huge issues in epitaxial growth, all the issues in contacts, all the issues in etching, heterostructures. All of these things have to come together. Because we have a bulk substrate for gallium oxide, these things have gone exceptionally fast for us. And so that just gives you some of the results. But this ideality factor is terrible for the dry etch. It's approaching what Shockley said should be the other ideality factor, which is 2 if you have trap-dominated recombination current as opposed to band-to-band. And in dry etch, it's down to 1.03, okay? So this is really exciting. Okay, now I'm gonna change gears because I think I'm about at the time of, okay. So I'm gonna skip forward and give you, I'm not gonna show you a lot of our work. We're incorporating new materials, new dielectrics into our work. This is beautiful work from Esmat Farzana and Nolan Hendricks, and some very surprising results. And just give you a summary. Looking at my concern, which is a big RPE project that I'm leading right now, is how we get 10 kV diodes, okay, that exceed the performance of any other semiconductor. Okay. All of these things are actually done now. So we can really check boxes on everything. I didn't talk about thermal management because it's a non-issue actually, and it's a sore issue. So I left it off here. But the one thing I really do worry about is the ability to have the really thick epitaxial layers with controlled doping, and preferably doing it in monolithic growth because the active region of the devices, we want to have different doping. And I'll show you what we're working on. So if you check our literature, if there's nothing on these devices in the next 3 or 4 years, then we'll failed. Okay. And okay, so this is actually what we're funded on from our new RPE program. The minimum requirement is that we have 3.3 kV Schottky diodes that are anti-parallel to something like a trench MOSFET, okay, which is also rated at 3.3 kV. We're optimistic that with thicker epi, with controlled doping, we can go beyond what is commercially available in silicon or silicon carbide and approaching the record diode results in silicon carbide for blocking voltage, okay? And so all of the pieces for this, except for these thick epi layers, are either demonstrated or in process, okay? But the other hard part of this is you go to an advanced device technology and want to be competitive with existing devices, and it's nice to just to beat them because that gets a lot more attention, is that, and this is really for device process physicists, processing these trench structures and sidewall structures and the edge of the structures with field management is really an art, okay? And then it's a dedicated, many tens of dedicated PhDs, okay? So even if you have something that's good and you can throw FOMs up and say, this is great, getting to this point of development turns out to be a massive effort, okay? And that's why I'm so glad to have a colleague like Sriram Krishnamurthy at UCSB, because at some point, making these structures, it's not for me. So anyway, okay. That's what we're working on.
Thank you, Jim. I have a two-fold question.
Yeah.
The first one is, in the epitaxial layer, when you're trying to dope the gallium oxide, do you expect that to be crystallographically similar as a bulk crystal? And I guess it's more of a disordered question. So you were talking about the two distinct sites that gallium, that the gallium oxides. So have you ever done anything? Yeah.
Donors.
Okay.
Yeah, donors. So silicon or germanium or tin in the donor case, right? And they go on one of the two gallium sites, right?
So I guess part of the question is, have you ever done a crystallographic study to see which, but you said the DFT predicts kind of either one or both. But I guess my question is, have you ever done a crystallographic study to see which site is actually preferred and how they either order or disorder, and to what extent across from silicon to tin? And how you can actually, could you actually get a numerical value for what you expect the end gap to be for a certain donor level, rather than some distribution based off of DFT?
Okay, so that's very packed. So, okay. So the most careful work, all of the most careful work, I should be careful. Most of the careful work in gallium oxide is on the most favorable crystal plane for growth, which is 0, 1, 0. For area, it's not the most favorable plane. The most favorable plane for area, just the way the EFG crystals are grown, is 0, 0, 1. So there's definitely a need, and this is what we're doing these days, is to do very careful doping studies on 0, 0, 1. Because that's the easily scalable substrate area, and see if we get the same ratio or different ratio shallow donor and slightly deeper donor, okay? So that's to be done. And we don't know if we can control the site that the donors go on or if they just naturally grow on the sites. But it's a great question, and it's well worth pursuing, okay? The band gap, the donor ionization energy, the band gap isn't going to change with doping, right? That's not a property that depends on doping, right? Yeah.
I wanted to talk about the figure there that you kind of the more modern version of it.
Simple rates.
Now, and so you obviously like basically it's very strongly influenced by the purity or donor like that. It's something that's
It's really, so what you get is, this is a conventional Ellicott figure of merit, and this is on resistance, just the length of the wire, okay, divided by the conductivity. The conduct N may not be equal to the donor concentration. And that's never was a flaw what Jay Balaga did. When he wrote his papers over 40 years ago, there were only semiconductors with shallow dopants, right? Because that was the era of semiconductor physics and device technology he came out of. Okay.
So the kind of point I get to is that so materials that you identified seem that nitride materials are not quite as readily accepted of new donors due to its like non-hydrogenic donor acceptance.
So GaN, so GaN has hydrogenic dopants. Okay, absolutely, they're hydrogenic. Okay, and what we mean by hydrogenic donors, for those of you who have some physics background, the original theory of hydrogenic dopants was done by Wanier in the 1930s, and Walter Kohn actually picked it up later. Okay, it's called effective mass theory. Okay, and you take an impurity, you put it into the semiconductor, you either extra or missing valence electrons, you build the electronic states out of the host lattice. And it turns out you, with a lot of math and a lot of pages of semiconductor physics, you come up with a very simple equation for the dopant ionization energy, and it depends on the host dielectric constant and the host effective mass. And the dopant looks like a hydrogen atom, and if you ionize it, it's just like ionizing a hydrogen atom. That's where hydrogenic comes from. That's why that's actually the basis of what's called effective mass theory. Okay, and many semiconductors within the last MeV have dopants that are absolutely hydrogenic. This is hydrogenic. This is hydrogenic. It's higher than this because you have a low dielectric constant in silicon. It just falls out beautiful. But many don't. Okay, and aluminum nitride doesn't, and diamond definitely doesn't. And one of the sites in gallium oxide is hydrogenic, and one is not hydrogenic. Yeah. We don't know. And so Chris van der Waal, we have a big fight on this. A couple of years ago, spent all of his DOE supercomputer budget to calculate, and he said everything. He said all the donors are hydrogenic and gallium oxide, and I don't know what you're measuring. So and because of dielectric constant, and you notice these numbers like here and here are quite similar because the effective masses are a little bit higher in gallium oxide than GaN, and the dielectric constants are about the same. Everything's about 10. So you get, very often you get this number that's on the order of 20 to 30 MeV for hydrogenic dopants. Okay. And for sure, one of the two sites is hydrogenic, but we don't know which one. And DFT's been unable to resolve it because it's not in the resolution, the energy resolution of the technique, basically. Yeah.
From gallium oxide, you're able to experimentally pull this information out, but if you're able to see that experimentally, but you don't have a solution to see which site.
I don't think, honestly, experimentally, I don't think we know which site. I'm sure folks that have much better crystal chemistry and tuition can make a very educated guess. I can't. Okay, I can't. Okay. But they're definitely two sites, and they really have this different, you see it because you get two slopes. Okay. You get quite often in the Arrhenius plots, you see two slopes, and that is a hint that when you go to the charge neutrality equation for fitting, these numbers are all fitted to the charge neutrality equation, which includes full carrier statistics. Okay, that you'll see two donor sites with different occupancies. Okay. Stop there. Thanks.